Okay, so I hope you can see the screen.
Yes, sir, we can see.
Mm. Yes, like so if you have multiple loops or the multiple meshes, so you basically can apply mesh equations. I mean, like so you can treat these two sub-circuit as two loops or two mesh and apply Kirchhoff voltage law, Kirchhoff current law by assuming this uh, branch currents I1, I2, and so on for node voltages like V1 and V2. So ultimately, you may ended up with multiple equations, and once you substitute appropriately, you can simplify these multiple equations and get a particular equation for the whatever the parameter you want to express. So you want to analyze. So for example, if you need to analyze V1, so you can replace, so ultimately you'll end up with two linear equations. So those two equations contains V1 and V2. So you just take, use one equation to obtain a value for V2 as a function of V1 and substitute it to the other one. So then you will end up with the equation for V1. So it's basically a kind of a differential equation. So we can discuss couple of examples, then you feel like, so whatever the complex circuit, if it is a first order circuit, you can simply get expression for the what the voltage or current in a certain branch. So once we go to this example, you may realize that. So what I want to highlight here is actually, so this circuit doesn't have any external sources, and this is basically powered by the initial condition of the circuit. So the initial condition of the circuit. So then, so for such circuit, this whatever the expression you obtain for the voltage or current is basically defined as the natural response of the circuit. So this is basically the natural response of the circuit. So natural response means the impact of the initial condition. Okay, so it means like if you connect an external source, so if you connect an external source, ext source, so the contribution coming from this external source is basically known as the force response. So if you have a circuit with external sources, the contribution or the impact coming from these external sources are defined as force response of the circuit. So if you have initial conditions, so if you have any initial conditions, it means like whatever the capacitor or inductor you consider here has a non-zero voltage or current. Yeah, sure. What if you have a capacitor inductor having non-zero initial conditions? So the contribution from these initial conditions is basically known as the natural response of the circuit. So then basically we have two responses. One is the force response, the other one is natural response. So the force response is basically coming from the external sources, and the natural response is basically coming from the initial conditions of the circuit. So the circuits which we are referring now doesn't have or do not have this external sources. So then the solution for this first order differential equation will ended up with natural responses only. So without sources leads to natural response only. So hope it's clear, because we whatever the circuits we discuss here, so they don't basically have these external sources. So then the driving force of the circuit is basically the initial conditions of the capacitor or inductor. So for such circuit, we'll ended up with a natural response. So if you have external sources, so particular circuit may ended up with either both natural response and forced response, or kind of a forced response only if your initial conditions are zero. So keep in mind, if you have external source, so you may have additional term coming to the picture which is known as forced response. So then in addition to that, you may have another VTR, VTF coming from these external sources. So this is known as the VNT, natural response. So this is the forced response. Ideally, any voltage or any parameter is a kind of a sum of the natural response plus the forced response. So keep in mind, so the always it's a sum of the forced response plus natural response. So if you don't have any external sources in the circuit, so you don't have this forced response. So this is basically zero. And VT or the whatever the measuring quantity would be ended up with the natural response only. So the circuits which we discuss now, they basically do not have external sources, so we can basically evaluate their natural responses. So the natural response is the contribution coming from the initial conditions. So what I want to highlight here is, okay, so we know that for these kind of circuits, so let's have this differential equation, A naught Vt equals 0. Okay, so let's assume like we have a kind of a trial solution like this. So this is the trial natural response. So we have a differential equation and we assume that there's a kind of a trial natural response in that model. So this is a kind of an exponential function. Okay, so if this trial solution or the trial natural response is a solution of this differential equation, which means once you substitute this Vt to the original differential equation, it should satisfy. So it means if you substitute this Vt to this original differential equation, it should satisfy. So it means like this. So the derivative of this plus A naught k e to the power st should be equals to 0. If this whatever the proposed trials or trial response is a solution of this differential equation, definitely this differential equation should satisfy with the voltage response we considered as a trial solution. So then this becomes like this. So here we have ks e to the power st, then a naught k e to the power st equals 0. So from this, you can take this common term out. So we know that if this k e to the power st is 0, so then you don't have any response. K e to the power st is 0, you don't have any response. So then definitely k e to the power st should not be equal to 0. Then we can simply say that s plus a naught is 0 and s should be equals to minus a naught. Okay, so what I want to highlight here is this expression. Okay, s plus a naught equals 0. Okay, so how do you, so this is known as the characteristic equation. So this is the characteristic equation of this differential equation. So if your differential equation is a first order differential equation, so you will end up with the first order characteristic equation. First order means for this linear expression, the order is again 1 or the maximum power is again 1. So if you have the first order differential equation, the characteristic equation also would be a first order equation. So it's a kind of a linear combination. S plus a naught equals 0. So this is the characteristic equation for the above first order differential equation. So this is the characteristic equation of the given first order differential equation. So without doing this calculation or this without having this trial solution, so we can immediately get the characteristic equation by substituting this. So the nth order derivative, if you replace the nth order derivative with s to the power n, if you replace the nth order derivative with s to the power n, you can immediately get the corresponding characteristic equation for this differential equation. So we have, so let's try it. So we have dvt or dt plus a naught vt equals 0. So how to get it? So we have first order derivative here. So we can replace this with s. Okay, because we have first order derivative here, so the n would be 1. So then you can replace it with s to the power 1 plus a naught. So this is the zeroth order derivative term. So zeroth order derivative term means n equals 0. So then you have s to the power 0, which is actually 1 equals 0. So see. So this is the substitution we can recommend here. So if you ended up with a differential equation, so keep in mind it should be in the standard form. So standard form means if it is a first order differential equation, so the first order term should be, or the coefficient of the first order term should be 1. So this should be matched with this format. So here you have 1. So otherwise it's not a first order differential equation. So you have to bring it to the standard form. Otherwise, whatever the coefficients you define here may be wrong. So keep in mind all the time, if you have non-zero, I mean like if you have a kind of a non-zero coefficient in front of this first order derivative term, it should be 1. If it is not equals to 1, you have to scale it to 1. So it means like if you have 2 times the derivative, you should basically divide the whole expression by 2. Okay. So for example, if you have like a1 dvt plus a naught vt equals 0, yeah. So then this a1, let's assume that this is not equal to 1. So what you can do is you can simply divide the whole expression by a1. So then it becomes dvt over dt. Here it's a naught divided by a1 vt equals 0. So now your a1 would be 1. So a0 ideally would be there. This is your a0. Okay. So the yes, like how did you get a naught? Yeah, a naught. So these coefficient, I mean, like I just use this I mean the symbolic format. So if you go to the previous example, which we have this capacitor and resistor, so we'll ended up with this kind of expression. Here you have 1 over RC Vt equals 0. Now this is your, so A1 is basically 1, A0 is 1 over RC. If you deal with the exact value of the circuit, so if you know the capacitance and if you know the resistance values of the circuit, so whatever the expression or whatever the differential equation you get in is basically with this known quantity. So A naught is a kind of a known quantity if you know the values of this capacitors and resistors. If it is unknown, it basically a function of whatever the parameters in the circuit. So for this example, so it basically comes as a function of R and C. Your A naught is a function of R and C. If you know this R and C exactly, you can basically found a numeric value for this A naught. Okay. Yes. Now we know how to obtain the differential equation. So how to obtain the differential equation means like if you apply Kirchhoff voltage law or Kirchhoff current law, you can basically write couple of equations and from those equations you can get a generic first order differential equation. If you get the first order differential equation, you can easily get the corresponding characteristic equation by substituting this. Nth order derivative can be replaced by s to the power n to get the characteristic equation. So if it is a first order differential equation, you will ended up with a kind of a linear characteristic equation, or again first order equation. So the characteristic equation again has a maximum power of 1. Okay. So then, so if now A naught is basically a function of R and C, like here. So then from this, we can basically get the value for S. So S is the exponent of the trial solution. So we started with a kind of a trial natural response. as a k function of exponential term. So k e to the power st. K is a kind of a constant and s also kind of a constant, which which is basically the exponent of the trial solution. So from this we can easily get the exponent. So this is the exponent of the response. So this quantity. Okay. So it means if you want to get the exponent of this trial solution, you can immediately convert your first order differential equation to its characteristic form and solve this characteristic form. So once you solve this characteristic form, it basically ended up with the value of s. For example, if it is a second order differential circuit, so if it is a second order differential circuit, according to our concept, this should end up with this kind of a quadratic form. So the characteristic equation would be a quadratic form. Quadratic form means s to the power 2. So it's like s to the power 2 plus kind of bs plus c equals 0. So the characteristic equation should be in the form of quadratic. So the power of this characteristic equation or the order of this characteristic equation is 2. So it means, so we can basically, if it is a quadratic equation or the second order equation, we can find two roots, s plus c1, s plus c2 equals 0. So for this case, you may have minus c1 s equals minus c2. So if it is a second order characteristic equation, in general, you may end up with two roots or solve two solutions for the second order differential equation. So if it is a second order, so then it means, so we have two exponential terms. So we have two exponential terms. So the exponential of the first trial solution would be minus c1. So the other one is minus c2. So it's like this. So you have k1 e to the power minus c1t plus k2 e to the power minus c2t. If it is a second order differential equation, you may have sum of two exponential terms. So the exponents of these two individual exponential functions basically comes as a root of the characteristic equation. Roots of the characteristic equation. If it is a first order differential equation, so you will end up with the first order characteristic equation like this. And once you solve this first order characteristic equation, you can easily evaluate or get the exponent of your trial solution, which is s. Okay. So how do you get this k is actually through the initial condition. If you know the initial conditions, you can just substitute it to this expression and get the solution. So for example, now we know that, so the trial solution is in the form of k e to the power st. So from characteristic equation, s plus a naught equals 0. So then s should be minus a naught. So we can find the exponent of pt. So this quantity, exponent means this is the one. So then our response would be looks like this: k e to the power minus a naught t. Now again we'll ended up with unknown constant k. So if you know the initial conditions, using initial conditions, so let's assume Vt t equals 0 is V naught. So this is your initial condition. So once you plug into this equation, so this becomes V naught. This is k e to the power 0. So once you substitute t equals 0, you will end up with k. So from this, we can basically evaluate the unknown coefficients. So then our ultimate response is V naught e to the power minus a naught t for this differential equation. Okay, so hope it's clear. So you can obtain the differential equation by applying Kirchhoff voltage law, Kirchhoff current law for a network. So once you anyhow mathematically simplify those equations, you can obtain a differential equation. If it is a first order circuit, definitely it would be ended up with a first order differential equation. If it is a second order, you will end up with a second order differential equation. If it is an nth order circuit, you will get the nth order differential equation. So once you get the first order differential equation, so you can easily evaluate the exponent of the trial solution by converting this into characteristic equation form. So how do you convert the characteristic differential equation to characteristic equation mode, CE mode? So just replace the nth order derivative with s to the power n. So then this becomes s plus a naught equals 0. So this is the characteristic equation. So then you can get, if you solve this one by solving the characteristic equation, you can find the value for s for the exponent. So the root of this characteristic equation, this is the root. If it is a first order equation, so you have basically a single root. So the root here is minus a naught. So the root actually comes as the exponent of the solution. So this is basically root of the root or roots of the characteristic equation. Characteristic equation. So then you can find k. You can find k using initial condition. For certain cases, equation itself gives the initial condition. For certain cases, you have to find the initial conditions of the circuit. Okay. So we'll discuss one or two examples, but keep in mind either you can find the initial conditions or sometimes it's given in the question. Okay, so then you can basically evaluate the unknown constant k by applying initial conditions. You can easily get the exponent of the response by converting your original differential equations to its characteristic equation form, and solve this characteristic equation leads to the you basically can find the exponent term or the unknown constant s. So it's the root or roots of the characteristic equation. So we'll discuss one example, so then you may get a kind of a better idea. Okay, I am yes, I'll take the exercise 1 in the slide set, EX1. So just try to obtain a differential equation for this circuit. So I'll give you. So you have R, you have L, this is current IT. Okay, so we have a kind of R, LO, LR circuit. So this particular circuit contains inductor and a resistor. So previously we have a capacitor and resistor. So now this particular circuit contains inductors and resistors. So LRO RL circuit. And here it says that the initial condition of the inductor at T, initial condition of the inductor means, so if it is an inductor, we are referring to a kind of an initial current. If it is a capacitor, we are referring to a kind of initial voltage. So here I, L, T at T equals 10 seconds is given as 3 amperes. So this is the initial condition of the inductor. So it anyhow measures the current at 10 seconds as 3 amperes. Okay. So this exercise asks you to prove that the natural response of the system is given by IT equals. So they ask you to evaluate the natural response or the current flow through the inductor or resistor 3e to the power minus 2 times t minus 10 amperes. So you need to evaluate or prove that the response of the circuit is like that. Okay. So how do you get this one? So if we mark the polarities, so if we mark the polarities of these two elements by considering the passive sign convention, so we can apply the Kirchhoff voltage law for this circuit. So then we can simply say that R times IT is the voltage drop across the resistor plus voltage drop across the inductor can be written as L DIT equals 0. So this is actually the voltage drop across resistor VR. So this is the L, voltage drop across the inductor. So from this one, you can easily get the differential equation like this. DIT or dt plus R divided by L IT equals 0. So this is the first order differential equation. Okay. So what about the time constant? For just sake of our knowledge, time constant of this LR circuit is the reciprocal of this zeroth order coefficient. So that's tau would be L over R. So the reciprocal of this first zeroth order coefficient. So this is the zeroth order term. So this is the zeroth order term. So this is zeroth order term. So if you take the coefficient extract from the differential equation and take the reciprocal, it gives the time constant. Yes. It's a reciprocal of the circuit. First zeroth coefficient. So the coefficient is actually R over L. So if it's clear, yeah. So in the previous case also, the coefficient would be 1 over RC, and the time constant of the RC circuit is actually R product of R and C. So similarly, you can extract the coefficient of the zeroth order term and take the reciprocal inverse 1 over. So then it becomes L over R. If you know the inductance value and the resistance value, you can immediately evaluate the time constant of the LR circuit. So now it's done. Okay, now we obtain a differential equation like this. So this basically, this differential equation explain the behavior of the current. So because it's a function of current IT, so then this first order differential equation explain the behavior of the current. So how do we get the natural response? Now get the natural response. So we know that this natural response is ultimately comes as form of this. So it's basically k times e to the power st. So the solution of this general first order differential equation is basically a kind of exponential function. So this is a non-factor. So this basically proving the differential equation module as well. So the solution for the first order differential equation be ideally a kind of a exponential function. So that's why we take this as a trial solution. So then we can find this exponent as find S. How do you find S? Convert this differential equation to its characteristic form. So characteristic equation. So how do you get the characteristic equation? So replace this nth order derivative with h to the power n. So we have first order derivative, so you can put s plus r over n equals 0. So this is the characteristic equation of this above differential equation. So then solving this, this characteristic equation gives the value of s. S equals minus r over s. Okay. So for this particular circuit, it's explained that your R is 2 ohm and inductance L is 1 Henry. So then R is 2 ohm and this is actually minus 2. So hope it's clear. So then your response IT is basically equals to a kind of a unknown constant. E to the power s becomes minus 2. Now it's e to the power minus 2t. So then find k. So this k, unknown constant. So how do you find k? substitute initial condition to the solution. So we basically obtain the solution as k times e to the power minus 2t. Now k is again unknown constant, so we need to find it out. So how do you find this unknown coefficient? So just substitute initial conditions to the solution we obtain. So initial condition or the current flow through the inductor, it's IT at t equals 10 seconds is equals to 3 ampere. So we can just substitute 3 ampere here. So 3 equals IT is 3 ampere equals 3 times, sorry, not 3 times, sorry, k times e to the power. So now t becomes 10, it's 20. T equals 10, so e to the power minus 20. So then k would be 3 e to the power 20. So hope it's k. So that negative exponent comes as a positive exponent. So k, your unknown coefficient or constant, it's equals to 3 times e to the power 20. So then we'll plug it to here. Your it now equals k is 3 e to the power 20, 3 e to the power 20. Then we have e to the power minus 2t. If you simplify it further, 3, so you can take e to the power minus 2 out. So then you have t here. So this e to the power 20 can be accommodated like this. So you have e to the power minus 2t into e to the power plus 20. So this is your current. So this is the natural response of the circuit. And if you ask to draw this response, it's something like this. So this is t, this is 0. Let's assume this is 10. So from here onwards, from 10 onwards, the behavior is something like that. For example, once you substitute t equals 10, so you have e to the power 0, which is equals to 1, then your current would be 3. So this is your value 3. So we don't know the past values. Sometimes from 0 to 10 seconds, the current may be 3 amperes. Or maybe it's a kind of a different value, but at t equals 10, your current would be 3 amperes. So we don't know the exact behavior of the circuit during 0 to 10 seconds. So we don't, so that's why we are not drawing the rest. So it may be like this, or it may be like this. So we don't know anything about, but we know the behavior of the circuit after 10 seconds exactly. It follows the 3 e to the power minus 2 times t minus 10. Can I explain how? This is like, so I am referring this exercise 1 in the slides. So there, so the circuit contains a 2 ohm resistor, R equals 2 ohm, and L equals 100. So I'm referring this exercise 1 in the slide say. So there it's basically referring a circuit where you have 2 ohm resistor and 100 inductor. So that's why I just substitute these two values and becomes this S as minus 2. Hope it's clear. Yes. Okay. So now the solution for this exercise 1 is this. So we prove that the behavior, the natural response varies like this: 3 to the power minus 2 times t minus 10, and the response is something like that. So you can basically precisely explain the behavior from 10 seconds onward. So we don't know anything about the previous situation, so you can keep that part as planned. But we know that from t equals 10 second onward, it's basically behave as a kind of exponentially decaying function. So this is the natural response. So we can get the exponent term by converting your original differential equation to the characteristic equation and solve it. And you can find the unknown constant k by substituting initial conditions to the circuit. So hope it's clear. So we'll move to another example. Okay, so now I am referring this exercise 3 in the slides, right? EX3. So before moving to that, I need to explain something else. So we know that for capacitor, so this is the equation or the model we obtained previously. So so this is C, this is C. So the induced current across the capacitor equals to C times the derivative of the voltage across the capacitor. Similarly, for inductor, the induced voltage across the inductor is equals to L times the derivative of the current. So I'll use subscript C and L to refer the voltages and current across the inductor, capacitor and inductor. So nothing else. So by looking at these equations, so we build a kind of a conclusion. What happens if these quantities are DC quantities? So we build a kind of a conclusion last time. So what happens if the voltage across the capacitor is a kind of constant value? So what happens if the current flow through the inductor is a constant value? So if we CT equals kind of a constant V, we know that the induced current goes to 0, and this capacitor can be replaced as an open circuit element. So this is already discussed. Similarly, for the inductor, if the current flow through the inductor is a kind of a constant DC value, so we can basically come to a conclusion like this. So the induced voltage is basically 0. So then there won't be any potential drop across the inductor. So then we can simply replace the inductor with a kind of a short circuit. So this is basically discussed in the previous section. So it means, so for this case, so we discuss a kind of a concept called DC steady state. So the DC steady state means, so we know that if we basically apply a DC voltage to a capacitor, so it's charged up to its maximum. So if it is a charging process, it's something like that. So it's charged it's to maximum and remains as it is. So we identify two regions there. So this is the charging of the capacitor. So during this position, during this segment, so this is a kind of a transient period. So during this transient period, the voltage across the capacitor is gradually increasing. From here onwards, we call this as a steady state. So once this capacitor comes to a steady state, means the voltage across the capacitor remains constant. So see, so I'm referring the charging process of the capacitor. Once you apply voltage across the capacitor, so it basically charged to the particular voltage. So if we analyze the behavior of the charging process, we found that during this 5 times tau, so the voltage across the capacitor is gradually increasing. So that particular time period we will call as a transient period. So during this transient period, the actual voltage across the capacitor is gradually increasing, or kind of we can say that exponentially increasing, or kind of. So it follows this trend. So it basically follows this trend. So this is gradually increasing. So once it comes to the steady state, so the voltage across the capacitor remains at a constant value. So once it comes to the steady state, it's basically constant. So it means if the capacitor comes to a steady state, so the actual voltage across the capacity is fixed and constant, and there won't be any current flow. So during this transient period, you can see a kind of a non-zero current flow according to this definition, because during this transient period, you can basically evaluate the derivative. So then your induced current is non-zero. Once it comes to a steady state, which means that the voltage across the capacitor fixed and constant, so the derivative becomes zero, and so during the steady state, the current flow through the capacitor is basically zero. So then we can argue that once your capacitor moves to the steady state, so there won't be any current flow through the capacitor, and capacitor can be replaced with the open circuit element. So the conclusion which we made here is, in DC steady state, capacitor can be replaced with open circuit element. In DC steady state, capacitor can be replaced with open circuit element. So keep in mind, this is valid only for the DC steady state. During this transient state, you can't replace the capacitor with the open circuit element. So our conclusion is basically, if your capacitor is in DC steady state, you can replace the capacitor with the open circuit element, because the impact of this capacitor is very similar to the open circuit, because there won't be any current flow. Similarly, you can argue that if it is an inductor, you can replace it with a short circuit element. If your inductor is in DC steady state, you can replace the inductor with a short circuit element, because the behavior of the inductor during this DC steady state is very similar to the short circuit element. Okay. Okay, done. So from this, we can make two conclusions. One is like, if the circuit is in DC steady state, all the capacitors in the circuit can be replaced with open circuit elements, and all the inductors of the circuit can be replaced with short circuit elements. So hope it's clear. So this is a kind of a conclusion we made when they are in DC steady state. So we'll then move to the circuit. Okay, we have okay. So Another point I need to highlight here. So we have switch like this. So what's the meaning of this? So this is basically this transition happens at t equals 0. So which means when t less than 0, so can you hear me? So still it's there. So can you hear me? Okay. So we have switch there in the circuit. So if you refer this exercise number 3, there's a switch. So we have switch like this.
Yes, sir, I can hear you.
Yeah, thanks. So I'm extracting the source and the switch. So we have a source and the rest of the circuit is basically connected to the circuit through a kind of a switch. So this is the switch I'm referring. Okay. So what happens? So what happens to the circuit during this t less than 0? It means before this particular switch moves to off state. So what happens at t equals 0? So this is moves to off state. Yeah, maybe due to this poor internet connectivity, so you may have kind of a delay. So at t equals 0, the switch moves to off state. It means this particular switch is basically at on state during the previous state. So once it moves to off state, before it moves to off state, so this particular switch was in on state. So it means, so t less than 0, your switch is basically in on state. So hope it's clear. So this particular switch basically operates at t equals 0 and moves to off state. So this arrow indicates the operation. So this arrow is out from the switch or this. So it means the switch is moves to off state. So if your arrow is something like that, so this means this basically moves from off to on. If your arrow is to the other way, so this basically moves from on to off. So keep in mind with the direction of the arrow, you can basically identify the previous states of the switch and the current state or the future state of the switch. So if your arrow is something like that, so it means the switch was in on state previously and moves to the off state at t equals 0. If your arrow is like that, it means the switch was in off state previously and moved to the on state. So then basically with this, we can identify two scenarios. if your switch so for this case, so initially this was in off and at equal 0 it moves to on. So this is means off to on. So this is basically moves from on to off. It means here for t less than 0, switch is in off state. T greater than or 0, switch is in on state. For this particular switch, t less than 0, switch was in on state, and t greater than or equal to 0, switch was in off state, pushed into off. So depending on the direction of this arrow, we can basically identify whether the switch was in on or off in the previous state. So what happens to the switch during this current position, and what happens to the state of the switch in future. Okay, so keep in mind everything depends on the direction of this arrow. Okay, hope it's clear. Now we'll move to the exercise. So we have 4 ohm, then 8, then 15. Source. This is 15, this is 8, 4, 2, 3. Here we have capacitor. It's a 1 farad capacitor. This is a. Now this question is this: assume that the circuit was in DC steady state just before the opening of the switch. So it means once you move this, change the status of the switch to off, so it was in DC steady state. It means, so we can argue that when t is less than 0, circuit was in DC steady state. So at t equals 0, you basically change the position of the switch to off. So this is like on to off, which means t less than 0. So this is in on state, t greater than or equals 0, this is in off state. So this is the information we can pick it from this by looking at the direction of the arrow. So then we can conclude that the circuit was in DC steady state when your t is less than 0. So now I am referring the past. So this is past, t less than 0. So then we know that if the circuit was in DC steady state, whatever the capacitors act as open circuit elements and inductors act as short circuit element. So we'll then draw the circuit when t less than 0. Okay. So I'm referring the same circuit. So what happens less than 0? So this switch is in on state. Here we have 15, 8, 4, 2 and another 3 here. So here the capacitor can be replaced at the open circuit element. So if it is open, so you don't need to draw it again. So nothing happens to the circuit. So now the circuit is this for t less than 0. Less than 0. So this capacitor acts as a kind of open circuit element. But we know that, so this capacitor is here. But for the simplification, once we simplify the circuit, we replace the capacitor with open circuit. But we know that this capacitor is basically happy across A and B. But the voltage across the capacitor is a kind of a constant, fixed constant DC value. So now we can find the exact voltage appear across AB and assume that that's the actual voltage appear across the capacitor when this switching happens. So it means from this, if you evaluate the voltage across A and B, so we can assume that this is equals to the capacitor voltage at t equals 0. So hope it's clear, because actually there's a capacitor in between A and B. But if the circuit was in DC steady state, so we can simply remove this capacitor or replace the capacitor with the open circuit element, because we know that if the circuit is in DC steady state, so the voltage across the capacitor is basically a constant and there won't be any induced current. So it's act as a kind of open circuit element. So based on that, we simplify the circuit, and if you want to find the actual voltage across the capacitor, you can find the voltage across A and B. It's the actual voltage across the capacitor when this switching happens, which means at t equals 0. So it's the voltage at t equals 0. So this is equals to VC0. So the initial condition of the capacitor at t equals 0. So how do you find this voltage across A and B? So now we don't have any capacitors in the circuit. So this particular circuit contains only resistor. So you can simply apply whatever the mechanism to find out the voltage across the capacitor. So the easiest way is like we can simplify the circuit. So this 4 ohm and 2 ohm are in series. So then you can combine this resistor. So then if you combine these two, so you have a 6 ohm resistor here. So then 6 ohm and 3 ohm are parallel. Okay. So then you can apply the parallel combination of resistors and simplify these two. So once you simplify this 6 ohm and 3 ohm which are in parallel, so the equivalent resistance would be 2 ohm. Okay. So that resistor is in series with 8 ohm. So then altogether we have 10 ohm in series with this 50. So if you simplify this block, so we have 10 ohm. Okay. So then A and B means the voltage drop appear across this 10 ohm. V at 10 ohm equals to V at across A and B. So by looking at this circuit, so the voltage across the A and B terminals is basically equals to the voltage across the 10 ohm resistor. So how do you get the voltage across 10 ohm resistor? So you can just apply voltage divider rule. Voltage divider rule to here. So we have 100 volt across this 10 and 15. So then we know that, so this 100 volt is proportionally split among this 10 and 15. So how do you get this? So VAB equals 10 divided by 10 plus 15 into 100. So which is equals to 40 volt. So actually there is a 40 volt appear across the 10 ohm resistor. So which is the actual voltage appear across the capacitor. So from this we can argue that this initial condition or the voltage across the capacitor at t equals 0 is 40. So hope it's clear. So you can easily get the initial condition of the capacitor. It is at t equals 0 as 40 volt. Now we have this information. We see t equals 0 equals, or we see 0 equals 40 volt. Now this particular circuit doesn't give any information about the initial condition, but with the DC steady state information, we can analyze the circuit and get the value for the initial condition of the capacitor. Okay. So now, so we need to evaluate the time constant of the resulting circuit and derive the, yeah. So we need to ask the voltage response across the capacitor. Now we basically analyze the initial condition by analyzing the circuit for t less than 0. Now we'll move to a circuit where t greater than or equals 0. So we use this circuit when t less than 0 to evaluate the initial condition. Evaluate the initial condition. So now we evaluate the initial condition and found that the initial voltage of the capacitor is 40 volt. Now t greater than 0. So if you draw the circuit, it's something like that. Sorry, this is because once we consider the t greater than 0 scenario, greater than or equal scenario, so this switch is basically most off state. So then the source in the circuit, so the source in the circuit is basically removed from the circuit because there won't be any impact because this is open. So its circuit is something like this. Okay, so then this the rest of the circuit is simply isolate from this 15 ohm resistor and this source because this is open, so there won't be any contribution from this 15 ohm. So then your circuit is basically simplified to this. This is t greater than or 0. So we evaluate this equivalent resistance here. So that's why this 10 ohm comes into the picture. So we have 10 ohm. So we can simply replace the equivalent resistance for this. This is 10 ohm. So then it's like you have a charged capacitor and a series connected resistor of 10 ohm. So we have a charged capacitor. So the initial charge is 40 volt and we have a 10 ohm resistor. So if you apply this Kirchhoff voltage source, so you can basically get this kind of expression. As 1 over RC. So R actually 10 ohm, C is 1 farad. So then this becomes 1 over 10 Vt equals to 0. Okay, so this is the differential equation which describe the voltage across this capacitor. dVt over dt plus 1 over 10 into Vt equals 0. So then, so we can easily get the characteristic equation. So how to get the characteristic equation? Replace the n derivative with s to the power n. So then this becomes s plus 1 over 10 equals 0. So this is the characteristic equation. So by solving this one, we can easily evaluate the roots of this characteristic equation, and it's the exponential of the, so exponent of the trial solution. So then we can simply say that Vt equals a kind of a constant e to the power minus 1 t over 10. So then it's a matter of finding this k. Okay. So how do you find the k? Find k. So we know that VC0 or the voltage across capacitor at T equals 0 is 40 volt. So we found that the voltage drop across the capacitor looks like this. So then substitute initial conditions. So then it's become 40 equals K. So then the natural response, so the voltage Vt equals 40 e to the power minus t over 10. So this is the response. So this is the natural response of the circuit. Natural response for t greater than or equals c. So it's 40 e to the power minus t over 10. So if you just draw it, it's something like that. So this is 40. This is the voltage across the capacitor. So what about the time constant? This time constant equals to 10 seconds. So this gives the time constant, RC product. So for this case, the time constant is 10 seconds and the natural response would be 40 to the power minus t over 10. So hope it's clear. So if you have any doubts, you can bring it to the forum. Okay, so then we'll move to the exercise 5. So we'll move to exercise 5. So I am referring this circuit. So I am referring the previous question. So this is one Vt initial condition of the capacity is 40 and the capacitance value is 1 farad. So we have 10 ohm resistor here. Okay. So if you remember, the first circuit we analyzed is very similar to this one. So we have a charged capacitor and a kind of a resistor which is seriously connected to the circuit. So if you apply Kirchhoff current law, we found that, yeah, so then for this particular circuit, so we have this RC product would be 10. So here you have 10 ohm resistor and 1 farad capacitor. So then the RC product would be simply 10. So if you apply Kirchhoff law, you can basically get this equation dVt over dt, and here you have 1 over RC. So this is 1 over 10 Vt. So you can apply Kirchhoff current law and get this equation, or else if you remember this one, or if you can refer this, just get it. But keep in mind, this is only valid for the single resistor, single capacitor scenarios, or single inductor, single resistor scenarios. If you have multiple resistors and capacitors, sometimes this is not the exact differential equation which explains the voltage across the capacitor. So keep mindful, like if you just apply, so you have to be very precise whether this formula or the differential equation is valid for this whatever the circuit you are referring. If it is a RC circuit containing a single equivalent resistor and a capacitor, this works fine. If you have a different circuit, this is not the differential equation explain the circuit. So for those scenarios, you have to apply the Kirchhoff current law, voltage law, and get the differential equation from the scratch. Okay, keep in mind that. Okay, so now we'll move to the exercise 5. Okay, you have a circuit. So you have a circuit having this 4 ohm, then you have switch here. And a current source of 9 amperes. Here we have 8 ohm. Here we have 4 ohm, 6 ohm, the capacitor here, 1 over 16 farad. Position 1, position 2, it's a kind of a rotary switch, and this is t equals 0. Okay. So these questions or the exercise describe the circuit. The circuit is in steady state at t equals 0 minus, which means just before this switching happens. So we, by looking at this operation, so we can simply say that t less than 0 was in position 1. T greater than or equals to 0 moves to position 2. So hope you can easily understand by looking at the arrow. Initially it was in position 1, and then at t equals 0 it basically moves to the position 2. So if you are analyzing the circuit when t less than 0, so you have to be mindful that this position of the switch was in position 1. So then at position 1, so this 9 ampere source is connected to the rest of the circuit. Once you move the switch in position to position 2, so if you move the switch to position 2, So then the rest of the circuit is basically isolate from the 9 ampere current source. So that's the difference between this one. So if it is in position 1, 9 ampere source is there. Once this switch moves to position 2, 9 ampere source is not in the circuit, rest of the circuit. So this is the information you can easily pick it from this. Okay. Okay. So then okay. So it is basically, it was in DC steady state at t equals 0 minus, and moves the switch to position 2 at t equals 0. So you can't see. How about now? Can you see the screen? Can you see the screen? Yeah, okay, done. So it basically says that t less than or less than 0 circuit,
Yes, sir, we can.
yeah, circuit is in DC steady state.
Yes, sir, we can see now.
Yeah. So then, so we can use this information to evaluate the circuit when t less than 0 to find out the initial condition of this capacitor. Okay. So now let's try to solve or analyze the circuit when t less than 0. So now I'm referring the same circuit, so it's easy for me. So now I'm referring t less than 0 case. So we know that for t less than 0, the switch was in position A. So it means the circuit is basically powered by this 9 ampere source. So we can simply say that it's something like that. It was in position A. The source 9 ampere source is basically connected to the circuit, and circuit is powered by this 9 ampere source. So the initial voltage of the capacitor is 0. So then what happens once you connect this 9 ampere source to the circuit? So it says that for t equals 0 minus, just before the switching happens, so the circuit comes to a DC steady state, which means this capacitor which means this particular capacitor can be replaced with the open circuit element, because now the circuit is in DC steady state. Okay, so now we'll replace it with open circuit element. But keep in mind, there is a capacitor here. So there is a capacitor here. But if it is in DC steady state, we can argue that this capacitor acts as an open circuit element. So that's why we replace this capacitor with open circuit element, but there's a capacitor here. Now, if you can easily evaluate the voltage across the capacitor. So for this particular question, so they basically ask the voltage across this 8 ohm resistor. But the problem is, for these resistors, we cannot define initial conditions because it's not an energy storing element. So we can define Initial conditions only for the energy storing elements, for these capacitors and inductors. So we cannot find the initial condition for this 8 ohm resistor here. So to evaluate the voltage across the 8 ohm resistor, we can start from here, because the real reason behind this is we cannot evaluate the initial condition for the resistors. So this initial condition would be basically for capacitors and inductors. So that's why we try to find the initial condition of the capacitors and use those information to find out the voltage across 8 ohm resistor. Okay, so we start from this end and simply moves to the voltage across the 8 ohm. So this is the circuit when this t less than 0. So then how do you find the actual voltage across the capacitor? So if you basically found the voltage across the 6 ohm, so it's exactly equals to the voltage across this capacitor or the voltage across this open circuit terminal. So to evaluate the voltage across 6 ohm, we need to find the current flow through this branch. Okay. So how do you find the current flow through this branch? So this is a current source. You can easily apply current divider rule. Apply divider rule. And the current flow through this branch, let's assume this is I. So IT is actually equals to 10 divided by 18 into 9. Okay. So the current flow through this branch is proportional to this resistance. Yeah, so this is 8. Okay, so hope it's clear. So the current flow through this branch is proportional to the resistor in the other branch. So this, so I and R are inversely proportional. So then 8 divided by the total resistance, 10 plus 8, 18 into 9. So this becomes 4 ampere. So the current flow through this branch is 4 ampere. So then the voltage across the 6 ohm is actually 6 into 4, 24. So then the open circuit voltage is actually 24 volt. 4 into 6, 24 volt. 24 volt induced across these two terminals. So this is like 4 amperes and this is 6 ohm. I into R, 40 volt, 24 volt. So then from this we can claim that VC 0 equals 24 volt. Or else we very precisely we can claim that VC0 minus equals 24. So according to the continuity theory across this capacitor, we found that voltage across the capacitor should be smooth and continuous. So from this we can basically claim that VC0 minus equals to VC0 equal to VC0 plus. It's again equals to 24. So based on the voltage continuation across the capacitor, we can argue like that. If we precisely write these answers. Otherwise, VC0 is actually 24. If we want to precisely explain this, this is the case. Based on the voltage continuity of the capacitor. So we explained in previous session. So this capacitor cannot manage this abrupt or sudden drops and rises in the voltage. So it should be like smooth and continuous. So based on that argument, we claim that so around a particular point, voltage should be equal. So based on that, we claim that V0 minus 0, 0 plus are equal in values. So now we found the initial condition of the capacitor as 24 volt. So it means once you connect this 9 ampere current source to the circuit and keep it for a certain times, this capacitor gets charged up to 24 volt. Okay, so this basically charged up to 24 volt. Now this capacitor basically, once you connect this 9 ampere source, it's basically charged up to 24 volt. So this is 24. So once it's charged to the 24 volt and comes to the DC steady state, so then we simply remove this 9 ampere source. So by placing your switch into position 2. So then we don't have any 9 ampere source in the circuit. So once you move the switch to position 2, so this 9 ampere source is simply isolated from the rest of the circuit. But at that time, t equals 0, at that time this is already charged to 24. Now this circuit acts as a circuit where we don't have external sources. So the circuit is self-powered by, and this self-powering comes from the stored energy of the capacitor. So from that onwards, we can see a kind of a discharging process through this whatever the resistors. Okay, so it basically charged up to 24 volt. Once it's charged to the 24 volt and comes to the steady state, we remove the source by positioning the switch to 2. So we basically move the switch to the position 2 and isolate the source from the circuit. So at that time, the capacity in the circuit is already charged to 24 volt. Now this circuit becomes a circuit where we don't have external sources, and the source is actually a capacitor. It acts as a kind of a virtual source temporarily with the stored energy of 24 volt. So then whatever the voltage inside the capacitor can be released through the rest of the resistors. So let's now see what happens to the circuit where t greater than 0. T greater than or equal to 0. So once it comes to the t greater than or equal to 0, so the switch moves to position 2, then the 9 ampere source is simply disconnected from the circuit. So now this is basically disconnected from the circuit. Okay. So we have a capacitor here. So now we have a capacitor here. It's there, and this is here the initial condition is 24 volt. Now we have a scenario where a circuit contains a kind of a resistors and a capacitors, and this capacitor is charged to 24 volt, and this 24 volt is basically driving the rest of the circuit. So hope it's clear. Now by looking at this one, this circuit can be easily simplified to this format. So these three resistors can be simplified to single resistor. So then you have a kind of a single resistor here, and we have a capacitor here. So this capacitor has a C of 1/16 farad. And what about the resistor? We have 4 ohm and 8 ohm are in series, so then the equivalent would be 12. So then 12 ohm is parallel with 16, so then it's become 12, 16, 4 ohm. Yeah, so the equivalent would be 4 ohm. So now we can simplify a circuit to a circuit where we have a single equivalent resistor of 4 ohm and a capacitor of 1 over 16 farad. So this capacity is basically charged to 24 volt at t equals 0. Now we need, this is the simplified version for t greater than or 0. So can immediately get the differential equation for this. So the differential equation basically explains dVt, voltage across the capacitor, plus 1 over now hope you can see the screen. So we have R4 yes. R is 4 and capacitor is 16. So this is like 4 Vt equals 0. dVt dt plus 4 Vt equals 0. Okay, from this one, so this is the differential equation which explains the behavior of the circuit. So from this, we can easily evaluate the voltage. So Vt can be written as e to the power st. So then, so we can get the characteristic equation. So the characteristic equation is s plus 4 equals 0. So the roots is basically minus 4. So then we can write the voltage across the capacitor as k e to the power minus 4t. Then by substituting the initial conditions, we can simply say that Vt equals 24 e to the power minus 4t. So this is the voltage across the circuit. So it means if you just put this information there, so here this is basically discharge in the form of, so the voltage across the capacitor is actually 24 e to the power minus 4t. So what about the voltage across this 8 ohm? So if this is the voltage across the capacitor, the same voltage appear across this resistor as well, the 6 ohm resistor. So it means voltage across these two terminals vary according to this. So what about the voltage across the 8 ohm? So you can just apply voltage divider rule to get the voltage across the 8 ohm resistor. So voltage across these two terminals is actually vary according to this. So then the voltage across 8 ohm Vt is actually 8 divided by 12, the total resistance, into VCT. So it's like 2, this is 3. So then 2 divided by 3 into 24 e to the power minus 40. So this is, so it becomes 16 e to the power minus 40. So this is the voltage across the 8 ohm resistor. So this is 16 minus 40. So that's why like we start from the capacitors and step into the voltage across Vt. So we cannot evaluate the initial condition for the resistors. So the initial conditions are valid only for capacitors and inductors. So we basically focus on the voltage across capacitors and inductors. So once you find this one, you can basically evaluate whatever the voltages across the other elements by applying current divider, voltage divider, Kirchhoff, or whatever. So the initial conditions cannot be evaluated for the resistor. So that's why we separately analyze the circuit for t less than 0 and evaluate the initial condition of the capacitor. So then use those information to evaluate the circuit when if it is in t greater than 0 case. So keep in mind all the time. So you have two states. One is t less than 0. So the other one is t greater than or equal 0. So we use this t less than 0 to evaluate initial conditions if those are not in the question. So then whatever the evaluated values can be substitute to the circuit which we are discussing for t greater than or equal 0. So so we basically analyze the circuit for t less than 0 to get the information about the initial conditions. Otherwise, no point of evaluating the circuit for t less than 0. So we are interested about this condition, t greater than or equals to what happens to the future. To evaluate the future response, we basically need the information about the past. To get this information which is valid for the past, we basically evaluate the circuit for t less than 0. So if it is less than 0, it basically explain whether the circuit is in DC steady state or not. If it is not, you can basically apply the same scenario, but you can't replace the capacitors and inductors with open circuit or short circuit element. You can keep the capacitors and inductors as it is and find the response. Then find the response, and if you want to evaluate the values, you just plug the value of t equals 0 to get this exact value of the capacitor. So what I want to highlight here is if those are not in DC steady state, so we know that this is the charging process of the capacitor. Okay, so we basically identify two regions. So this is the transient region. So this is the steady state. So we know that once this capacitor comes to the steady state, this is the voltage. So we can easily evaluate the steady state voltage by replacing capacitors with open circuit element and inductors with short circuit element. So then it's fine. But if your switching happens during this transient state, this circuit is not reached to steady state. So for example, you basically switch this circuit at this point. So then you cannot treat the circuit which is in transient state by replacing these capacitors with open circuit elements. So then you have to keep the capacitors and then inductors as it is and find the response. Find the response means this equation. So it would be like a kind of a function. So then just substitute t equals 0 to that function and get the value at this point. So for that, it's not easy. So you have to do the similar kind of analysis like we did for t greater than or equal to 0, for t less than is 0 as well. So if it is DC steady state only, you can just replace capacitors and inductors as we discussed. If it is not mentioned, so I have to think that the circuit is in capacitors and inductors which are in the transient state cannot be replaced with the open circuit or short circuit element. So then you have to keep the capacitance and inductors as it is and apply Kirchhoff voltage laws and get the differential equation and solve the differential equation and find the voltage or current response. Then substitute respective values for t to get the exact value at this point. If it is moves to steady state only, we can do the kind of a simple calculation and get the initial conditions. Otherwise, you have to do the similar calculation which we do for this t greater than 0 for as well. Okay. So any questions so far? If not, we will move to the slide number 15. So now we move to the scenario where we have with sources. Okay, so I'll use a very simple circuit. So we have a RC circuit which is basically connected to a kind of a current source, DC current source. And we are asked to analyze the circuit. So we'll try to do that. So if those elements are in parallel, so the wise way of solving this is basically apply Kirchhoff current law. Because all these elements are connected to these two common nodes. So rather working with voltage law, it's wise to use current law because we can easily identify the nodes. Because all the elements are in parallel. If we have a kind of a mix of series and parallel, so you can use either Kirchhoff current law or Kirchhoff voltage law. If you have a lot of series connections, so better to start with Kirchhoff voltage law. If you have this kind of a parallel set of elements, so wise to start with Kirchhoff current law. So we'll apply Kirchhoff current law. So this I naught comes into the node and we basically mark this rest of the currents which will leaving from the node. Okay, so we'll apply Kirchhoff current law. So the current flow through the capacitor so can be written as d vt over dt. So this is the current flow through the capacitor. I equals C times the derivative of the voltage. So then this is also leaving from the node plus, so the current flow through the resistor is actually Vt divided by R. So the Vt is appear across the resistor. So then Vt divided by R, which is equals to I naught. So currents leaving from the node equals to the current flowing to the node. So then we basically rewrite this equation, which is aligned with the first order differential equation. To make it first order differential equation, so you have to make this coefficient 1. The first order derivative, the coefficients of the first order derivative should be 1. So we have C here. So we basically divide the entire equation by C. So then it becomes the derivative of the voltage plus 1 over RC Vt equals I naught over C. Okay. So this is the differential equation. Now previously, so in the previous scenario, we got this kind of equation. So now we have additional term appearing in the right hand side of the differential equation. So when we are discussing this circuits without external DC sources, we will ended up with this kind of a first order differential equation where your right hand side is 0. Once it comes to the sources, so your right hand side is basically not equals to 0. It's with certain values, which is actually if you look at the quantity appearing in the right hand side, so this I naught is the value of the current source. See? So then it means whatever the values appear in the right hand side, so whatever the values appear in the right hand side always indicate the contribution of external sources. So I believe like you got the point. So initially when we were discussing this circuits without sources, your right hand side would be simply 0. So once you move to a circuit where you have external DC sources, so the contribution of the DC sources are simply concat to the right hand side of the differential equation. So then we can argue that, so in the differential equation, the right hand side of the differential equation basically comes from the external sources you plug into the circuit. Okay, so then if the right hand side is non-zero, it means your circuit definitely contains external sources. So the contribution of these external sources are simply appear in the right hand side of the differential equation. So hope it's clear. So if this right hand side is 0, if the right hand side is 0, it means no any external sources. If your right hand side is non-zero, so you have external sources. So definitely then you can double check whether the differential equation you obtain here is correct or wrong. by looking at the circuit. If you have external sources in the circuit which you are analyzing here, definitely your right hand side should be non-zero. If it is zero, it means your circuit is basically do not have any external sources. So then we discuss a scenario where we don't have external sources. So for this case, we found that so this particular VT has a natural response. So natural response means the contribution of initial conditions. Okay. So if you have natural response, it means it basically captures the initial contribution of the initial condition. So if you basically solve a differential equation which has a zero in the right hand side, so you have natural response only, and you can basically get the natural response easily by converting it to a characteristic equation and substituting initial conditions and so on. So we discussed it previously. Now we have a differential equation where your right hand side also having non-zero quantities. We identified that the right hand side is basically managed by the external sources you plug into the circuit. So this contribution, the contribution from these external sources are known as actually a forced response. So forced response means once you plug the external source, so this source you connect to the circuit forced to behave according to its value. If you connect a charged capacitor inductor to the circuit, naturally the circuit behave according to the capacitor's initial condition. So it becomes a natural response. Once you connect a circuit, it basically forces the circuit to operate as the source wish, or as the source according to the values of source. So the contribution of the source comes to the picture as a forced response, and the contribution of the initial condition of the energy storing elements, capacitors and inductors, are coming to the picture as a natural response. So then ideally any response xt is a combination of these two, xnt plus xft, natural response plus the forced response. So the combination of these natural and forced responses give the entire response of the circuit, or the total response of the circuit. Now if we have these sources in the circuit, so we need to evaluate these two quantities. One is the natural response, so the other one is the forced response. Okay, now we'll move to, so now we have this kind of a scenario. So now your differential equation looks like this. Okay, so you have a non-zero right hand side. Okay, so you can first evaluate the natural response. So how do you evaluate the natural response? So how do you evaluate the natural response? Yes. Yeah, natural response means so the contribution of the initial condition. So then we can ignore the impact of the external sources we add into the circuit. So it means, so we know that the contribution of the external sources are simply concurred to the right hand side of the differential equation. So by letting your right hand side to be 0, so you can simply ignore the impact of the external sources. So then let C to be 0. Okay. So once you let the C or the right hand side of the differential equation it to be 0, so you can simply ignore the contribution from external sources and analyze the effect of the initial condition. So then your differential equations look like this. So this is very similar to the discussion we had previously for the scenario where we don't have any external sources. So first what we can do is convert to characteristic equation. So then it becomes S plus A naught equals 0. So this is the first order differential equation. So you will end up with the first order linear equation. So then once you solve this characteristic equation, so you can basically get the exponent term of the response. So then this becomes Vt equals k e to the power minus a naught t. So then apply initial conditions. Okay. So then basically you can apply the initial condition. So we'll stop at this point because there is a impact from the source as well. Okay. So then how do you find the force response? Okay. How do you find the force response? So let's assume, so there may be multiple possibilities now. First is C equals 0. No, not short circuit. Actually what we can, so we can identify different cases. One is C equals 0. So for C equals 0, we know that no force response. Because C equals 0 means no any external sources, no such impact on the circuit. So this VFT force response is 0. So the second case, C become a kind of a constant. So C becomes a kind of a constant. So it means you have DC sources in the circuit. So if your right hand side is a kind of a constant, like in the example we discussed just before, so it's like I naught divided by C. I naught is the value of the DC current source, C is the capacitor. So this is basically a kind of a constant. So then our argument is very precise. So we know that the circuit contains DC sources. We had this DC current source of I naught. So if your right hand side ended up with a kind of a constant, so it basically contains DC sources. Okay. So the third scenario, C is a kind of a time varying function. So then you have AC sources in the circuit. Okay. Got the point? You have AC sources in the circuit. If C equals a kind of a time varying function, you have AC sources in the circuit. So these three scenarios or three categories can be identified. C equals 0, no external sources, forced response is 0. So C becomes a kind of a constant. So then you have DC sources in the circuit. So C is a kind of a time dependent quantity or function of time. So then you can claim that whatever the sources you plug into the circuit is a kind of a time varying sources. Like for example, if you connect a kind of a current voltage source Vm sine omega t, so this is your voltage source you plug into the circuit, or this instead of I naught, if you have this Im cos omega t, so then you definitely ended up with the right hand side with the time dependent quantity. So if this I naught is a kind of a Im cos omega t, so ideally it be ended up with this kind of a value, Im cos omega t divided by 0. C. So then it's a kind of a function of time. So then we can argue that, so these particular sources are not DC, so they are basically AC sources. Okay, so we identify three scenarios. So then, as in the previous case, we can try out with a kind of a trial solution for the forced response as well. Okay, so like in the previous case, once we are dealing with natural response, we came with a kind of a trial natural response, which is equals to k e to the power st. So then if it is a kind of a solution of this differential equation, it should satisfy. Based on that assumption, we substitute the trial solution to the original differential equation and come with a kind of a value for the exponent. So it can be alternatively found through the characteristic equation. So this is the discussion we had couple of hours before. So similarly, for the forced response as well, we can come up with a kind of a trial solution depending on the format of the source. Okay, depending on the format of the source. So we can come with the trial solution, trial force response, depending on the source. Okay, so why I simply say it's depend on the source. So the trial solution would be aligned or synchronized with the format of the source. If it is a constant, if C is a constant, or the right hand side, I'll put right hand side. Right hand side of the differential equation is constant. You can propose a forced response as another constant, like A is a constant. Okay, so if your right hand side is a kind of a time varying function, you can propose a trial forced response which is sync with ft. So what I mean sync is, like for example, if your right hand side, or if your right hand side, so which is known as forced term, if your forced term or the right hand side contains cost functions, you can propose a kind of a forced trial solution response as A cos same frequency plus B sine same frequency. So this is the more generic form of the sine cosine function. So then you can find A and B and precisely evaluate what is the ultimate force response. But if you are proposing a trial solution, it should be synchronized with the pattern of the force term or the right hand side, and your trial response would be more generic way of aligning with the force term. For example, if your right hand side is a kind of a exponential function EAT, like 3 EAT, so then your force response would be a kind of KEAT, kind of a constant followed by the same exponential. So we will discuss this scenario separately, but for the time being we'll deal with this DC sources. So then your right hand side definitely ended up with a kind of a constant. So then the trial solution for the force response would be another constant. So keep in mind for the moment. So we'll discuss this time varying quantities later. For the time being, so we are dealing with external DC sources only. So then your right hand side definitely would be a kind of a constant, because we know that right hand side or the force term is a kind of, it basically appear as a contribution of the external sources we plug into the circuit. So if we connect the DC sources, definitely your right hand side or the force term would be a kind of a constant. So if your right hand side is a constant, your trial force response would be again a kind of a constant. So we'll see how to evaluate this. Now, so this is our differential equation. C. So now C is a constant. So we find force response. So we'll put VFT. So first we start with the trial solution. Trial force response. So we propose a trial force response by looking at this right hand side. So it's a constant, so then we propose our trial force response as a kind of a constant. A is a constant. Okay, so then if this trial solution is a trial response is a solution of this differential equation, definitely this should be satisfy the original differential equation. So once you substitute this force response to the original differential equation, it should satisfy. So then d over dt, a constant A plus A naught Vt is kind of a constant, should equals to the C constant. So this is basically 0, constant of the derivative of the constant. So from this we can simply say that A is C divided by A naught. So then from this we can claim that force response VFT equals C divided by A naught. Okay. So now we found the force response, C divided by A naught. This is the force response. So according to our justification, if your right hand side is a kind of a constant, definitely your force response would be a kind of a constant. So we found that our force response is equals to C divided by A naught. C is a constant, A naught also a kind of a constant which depends on the RCL value of the circuit. So then ultimately we'll end up with a kind of a constant value for the force response. So we start with the natural response there. Find natural response. Find V and T. So to find the natural response, so we set or let the C to be 0. because we remove the impact contribution from external sources. So then our differential equation simplifies to this form. So then we similarly we propose a trial solution as Vnt as a k e to the power st. So we found that we can easily find s by getting the characteristic equation. So this characteristic equation is s plus a naught equals to 0. Solving this characteristic equation, we can get the exponent term. So then this Vnt becomes k e to the power minus a naught. So this is your forced response. So this is the natural response, but we still have this unknown constant. Okay. Now previously, if we had only natural response, we immediately substitute natural initial condition to the circuit to find this unknown value k. But if you have this natural and forced responses are there in the circuit, so you cannot apply initial condition at this stage, because we know that the ultimate response is a sum of these two. So then initial condition also basically impact by the sources. So if you refer the circuit, so initial condition of the circuit also may be impact from the circuit, DC sources. So we cannot just apply initial condition by ignoring the forced response. So keep in mind for these cases where you have both forced response and natural response, so you cannot plug the initial condition by ignoring the forced response. So then, based on that argument, we can claim that the total response Vt is the sum of natural response and the forced response. So the natural response is k times e to the power minus a naught t, plus the forced response is c divided by a naught. So this is the total response. So once you obtain this one, then you can apply initial condition to get the value of k. So keep in mind, so you cannot immediately evaluate the constants of the natural response without ignoring the forced response. So then you can just apply, like let's assume like Vt at t equals 0 equals V naught. So then V naught equals k plus c divided by a naught. So then k equals V naught minus c over a naught. So then if you plug it to here, your Vt total response equals V naught minus c over a naught into e to the power minus a naught t plus c over a naught. Okay, so this is the exact response. Okay, so hope it's clear. So if once you have these external sources, external DC sources in the circuit, just apply the Kirchhoff voltage or current laws as we started in the previous. So then gets the differential equation. Basically it's a first order differential equation because we are now focusing on first order circuit. So the difference between the previous and the now is like your right hand side of the differential equation is not a zero, so it's come with a kind of a constant. So if it is a kind of a constant, so we know that there is a kind of an impact or the contribution from external DC sources. So if you have a kind of a differential equation having a non-zero constant in the right hand side, so we basically need to find these two quantities. One is the natural response, which is the contribution of the initial condition of these capacitors and inductors, and the force response coming from the external force sources we plug into the circuit. If it is if your right hand side is a kind of a constant, you can propose a kind of a trial force response as a kind of a constant again, which is different from the constant which is in the differential equation. So like in this case, we can propose a kind of a constant as a trial force response, which is equals to capital A. So if this trial force response is a solution of this differential equation, it should satisfy the original differential equation. So by using that, we can easily find the value of this constant. So just plug this trial response to the original differential equation and find the value of A. So then we found that A is actually C divided by A naught. C is the right hand side of the differential equation and A naught is the first zeroth order coefficient. So don't keep this equation in your mind. So you should start with the stretch. So apply Kirchhoff voltage or current law and get the equation and remodify it to until you get the standard first order differential equation. Then apply these trial solutions and get. So you don't keep this equation in mind. So these equations are completely different from the circuit which we are referring. So no point of memorizing those. Start with the Kirchhoff equation, get the differential equation. Once your differential equation has a non-zero constant in the right hand side, so then you feel like you have to evaluate two quantities. One is the force response of the circuit, which counts the contribution of the external sources. If you have initial condition of the circuit, then definitely you have a natural response as well. So how do you find the force response? So if it is a constant, your right hand side of the differential equation is a constant, you propose a trial solution as again another constant. So then substitute that to the original differential equation and find the constant value of this. So then you can find the natural response by letting your right hand side or the force term to zero. So then your differential equation has a zero quantity in the right hand side. So then again your trial response for this kind of equation is kind of a k e to the power st. So you can find the exponent by converting this differential equation to the characteristic equation. So solving this characteristic equation, you can immediately find the exponent of the natural response. So then we can argue that the total response would be the sum of the natural plus sum of the natural and force, like here. So this is the total response. So then once you plug this natural and force response, you obtain here to this. And then only you can apply initial condition to find the K. So keep in mind, if you have both responses in the circuit, so once you find these two responses without this K, so then after that only you can apply the initial conditions to evaluate the K value. So you can't evaluate K here. So you can't evaluate the K here. Because it means, so once you evaluate the K here, you basically ignore the impact of the force or the external sources to the initial conditions as well. So to avoid that, you can take these two responses separately and write down the total response by summing these two quantities, then only apply the initial conditions to get the unknown constants. Okay, we'll try one example. So then you will be clear on that. Okay, I am referring exercise 5. exercise 5. Okay, so we have a circuit like this. We have 2 ohm resistor. So then we have a switch 4 ohm. An inductor here, 1 Henry inductor, 16-volt source, here 12-volt source, 2 ohm, 4 ohm, T equals 0. So you are asked to evaluate this I. Okay, so so the circuit question explained that assuming that this circuit has had sufficient time to go to DC steady state prior to t equals 0. So determine the response of the inductor. Okay. So then, so we found that we don't have initial conditions of the inductor, so we need to find the initial condition of the inductor as well to find the exact response of this one. Then we'll go to this t less than 0. So what happens t less than 0? So this switch is basically at on state. So switch was at on state. When we deal with t less than 0, so the circuit is, the switch was at on state. So then we have these 2 sources in the circuit. Okay. So then again, other than that, we know that this is in DC steady state. So if the circuit is in DC steady state, what we can do, we can replace this inductor using a short circuit element. We'll replace this inductor using short circuit element. But keep in mind there's an inductor here. But for the DC steady state, we can replace the inductor with a short circuit element. Now we can find the current flow through this inductor. So it means the current flow through this branch. How do you find the current flow? So what about the current flow through this branch? It's actually 12 divided by 2. So this is a 0 potential. So then the current flow through the resistor would be 12. Here you have 12 volt. This is ideally 0 volt. So then the current flow through the resistor is 12 divided by 2. Voltage divided by the resistance. So it basically flows through the short circuit part. Similarly, you can find the current flow through this resistor as well. So this is basically 16 divided by 4. So then the total current flow through the short circuit path is 12 divided by 2 plus 16 divided by 4. So then IL0 is actually 12 divided by 2 plus 16 divided by 4, which is equals to 10 amperes. So then the current flow through the inductor, when it is in DC steady state, actually 10 amperes. So now we found the initial condition of the inductor to find the exact response of the inductor. Now we'll move to the next. T greater than or equal to 0. So in that case, so the switch is now at off state. So once you move your switch to off state, so we'll ended up with this kind of a circuit. So this whatever the 16-volt source is, simply disconnect from the rest of the circuit where you have inductor. So then you have this 2 ohm resistor, here you have an inductor, and you have a source here. This is like 12 volt. So this is like 2 ohm, this is 1 Henry, and IL0 equals 10 amperes. Okay, so see, like for the initial condition of the inductor, so both this 12 volt source and 16 volt source contribute. So that's why, so in the previous discussion we apply initial condition after we found the forced response as well. So the forced response also, I mean, like the external sources you plug into the source basically influence to the initial condition of the circuit. So that's why we apply initial conditions after we found the forced response as well. So if you just apply the initial condition before you find the forced response, it gives a wrong answer, because from this example we felt like this initial condition of the inductor or the initial current through the inductor basically handled by the 12 volt DC source and the 16 volt DC source. Okay, so that's why we apply initial conditions after we found the forced response. Keep in mind, otherwise whatever the constant values you obtain in your as a solution is completely wrong. So now when t greater than or equals 0 case, we found that, so we have a circuit containing a 12 volt DC source and a 2 ohm resistance and the 1 Henry inductor having an initial condition of 10 ampere. Okay, so now how do we solve it? So for this case, we can easily apply Kirchhoff voltage law. Okay, so you can mark the currents and voltages. Like for example, if I just want this is your current. Okay, so we can simply apply these values. Okay. So the so once you apply Kirchhoff voltage law, we can simply say that IT into 2 ohm, which is the voltage drop across this resistor. So plus minus. So then the induced voltage across the inductor is actually L times the derivative of the current. L here is 1. The derivative of the current. So these two voltages are equals to 12 volt. So then we can simply say that the IT over dt plus 2 times IT equals to it. So this is the differential equation which explains this simple circuit for t greater than or equal to 0. So then we can find the two responses, natural response and forced response. So forced response, so this is a current, so you can use IF, current forced response. So you can propose a trial solution as a constant, IFT is a constant. So once you plug it to the original differential equation, we found that 2 times A equals 12. So then A becomes 6. Okay, so then your forced response equals 6. Your forced response is 6. So then you move to the natural response. So letting your right hand side to be 0, then your differential equation would be this plus 2it equals 0. So then the characteristic equation would be s plus 2 equals 0. Then once you solve it, it becomes s minus 2. So then the natural response int equals k, which is unknown constant, e to the power minus 2t. So from these two, we can find the total response. Now this total response IT is a sum of INT plus IFT. INT is k e to the power minus 2t. This is 6. So then apply initial conditions. So we know that IL0 equals 10 amperes. So just substitute 10 equals k plus 6. So the k equals 4. So then the ultimate total response is equals to 4 e to the power minus 2t plus 6. So this is the, so if you draw it, at t equals 0, so this exponential would be 1, so then you have 10 here. Okay, so then once this goes to t goes to infinity, e to the power minus 2t goes to 0. So this becomes 0 now. So then the response would be something like that. Okay. So initially start at 10 and it converges to 6. Okay. So we found that the total response is equals to sum of this natural and force. And this natural response is a kind of a function of e to the power st. What happens it when t goes to infinity? So when t goes to infinity, so the natural response converges to 0 because it's an exponential term. So once t goes to infinity, your exponential term decays to 0. And it converges to IFT. So what is the conclusion we can make out of this? If you have a natural total response, which is a sum of the natural response and forced response, the steady state response, steady state response. State response means once what happens to the response when t goes to infinity. So the mathematically, what happens to the response when t goes to infinity? So it's the steady state response after a reasonably fair enough long time. So the total response converges to forced response. So this is the conclusion we can made out of this discussion. Your total response is the sum of natural plus force. If you are asked to evaluate the steady state response, so we know that the steady state response is actually converged to forced response. So if I ask to evaluate the steady state response, so you don't need to evaluate the natural response even, because we know that from this expression, we can simply say that the steady state response means your total response is basically converged to forced response. So then it's enough to find the forced response only, if it is a steady state response. If you are asked to evaluate the total response or just the response, so you have to find the natural plus the force, both. If you ask to evaluate the steady state response, we know that the steady state response is the forced response. So then it's enough to find the forced response. So it's basically explained here. So this is the total response we found for the previous circuit. So it's 4e to the power minus 2t plus 6. So once you plot this, we can basically realize that once this t goes to infinity, the total response basically converges to 6. 6 ampere is the forced response of the circuit. Okay. So then this basically, so this is the steady state. So this is the steady state response. So it basically equals to IFT, forced response. Any questions so far? Until Vishnu comes. Yes, okay. So we'll have the class on Monday, 1 to 3. I guess you don't have any exams during that. Yeah, so how do you get the characteristic equation is very simple. If you have a differential equation, so let's have this differential equation. So this is your differential equation. Replace the nth derivative by s to the power n. It means n equals 1 means first order derivatives replaced by s to the power 1. Second order derivatives replaced by s to the power 2. Zeroth order derivative replaced by 1. So then it's like d over dt is basically replaced with s. So this, how this d over dt 0 means zeroth order derivatives. This is the zeroth order derivative replaced with 1. So then this dv over dt is basically replaced with s plus a naught. So this et is the zeroth order derivative. It's just a function, not a derivative. So then it's replaced with 1. So s plus a naught equals 0 is the characteristic equation for the above one. For example, let's think about this scenario. So you have d squared vt over dt plus 2d plus 3vt equals 0. So if you want to get the characteristic equation, so this become s squared. So this is the second order derivative. So we replace it with s to the power 2, then 2 times. So this is the first order derivative. So we replace with s, then 3. So this is the zeroth order derivative. So we replace it. So then this is the characteristic equation. Okay, so this is the way you can easily get the characteristic equation. Keep in mind, if you have this right hand side non-zero when we are dealing with the external sources scenario, so the how do you get the characteristic equation is because characteristic equation we basically find it for the natural response. So then you have to ignore the impact of sources. So then first you have to let your right hand side of the original differential equation to be 0, then apply this replacement or the substitution. Otherwise you will end up with a kind of a non-zero quantity in the right hand side of the characteristic equation. So keep in mind all the time this this characteristic equation is coming to the stage when you are evaluating natural response. Natural response means the contribution of the initial conditions without any influence from the external sources. So then first you have to set the right hand side of the original differential equation to 0, then only you can replace this derivative with s to the power terms to get the characteristic equation. Otherwise your right hand side would be non-zero quantity. Okay, keep in mind all the time characteristic equation, definitely your right hand side should be 0. So to make it 0, first you start with the differential equation and set the first term or the right hand side to be 0 and then convert it to s function by replacing all these nth order derivatives to the power n's dt n's with s to the power n. Okay, so hope it's clear. Yeah. So then I got a request through your batch representative, and we move the exams, both analog and circuit exams, to the Friday, 4th December from 9 to 10:30 on 4th day, Friday. Circuit analysis 2. So it basically contains 3 questions, 30 for each. So then 11, how to write the natural response? Yeah, so we basically discuss this in the second order circuit. So yes, if you want to get the natural response, so this is your characteristic equation. So this is quadratic equation. So then you basically ended up with 2 roots. So this is a quadratic equation now. Varga samikaranak, once you solve this Varga samikaranak, you'll end up with 2 roots. So then you can basically write this natural response like this: k1 e to the power a1t plus k2, another constant, e to the power a2t. So this is the natural response of the second order circuit or second order differential equation. But again, like we can further simplify because we know that, so depending on the roots, so if you go through this roots of the quadratic equations, so we can identify 3 scenarios. One is you may have distinct roots. So it means like A1 real and distinct root. So this A1 and A2 are real and they are like 2 different values like this. So S is -1 and -3. So these are real distinct roots. So for the roots for a quadratic equation, you may come with this real distinct root. So then the ideal solution is this. if you have equal real roots like -1, -1, so then you can simplify this format to further level. If you have complex root, so then you will ended up with a kind of a different solution. So everything based on this, the types of the roots, but in general you can write the natural response as a sum of two exponential functions. But you can further simplify this to sum of this exponential function by considering the format of the roots, whether they are real and distinct, or whether they are real and equal, or whether they are complex conjugate. So then the responses would be completely different. So we will discuss it in the second order circuits. For the time being, if your characteristic equation is a kind of a linear equation having the first order, so the order of the characteristic equation is simply 1. So then you will ended up with a single root. So the single root appears as an exponential function in your natural response. So nothing else. So then we'll have 11 to 12 for analog electronics 1. Analog electronics 1. So analog electronic 1 basically covers up to voltage multipliers. So I'll discuss this voltage multipliers in Monday during this normal lecture slot. And for this circuit analysis 2, so we'll basically covers up to a circuits with and without DC sources. So it basically covers up to that. So basically covers to the slide number 20. Yes. Slide number 20 in this first order circuit. Hope it's clear. Any questions? So do you have anything to clarify? No, this Monday you don't have any exam. I mean, like, so you may have this differential equation exam, but this analog midterm, due to the request coming from you people, I push it to the Friday because you had a concern like, so then it's hard to sit for the back-to-back 2 modules. So you have differential equation from the morning 9 to 11, then from so it's not feasible. So I'll move the 2 midterm exams to Friday, 4th December, and the morning 9 to 10:30 we have this circuit analysis 2. Then after a 30 minutes break, we can have this analog electronics 1 midterm. Okay. So if you don't have any questions, so shall we wind up the session? Yeah. Okay, then thank you. I'll upload these 2 videos.
Thank you, sir.
Thank you, sir.
Yeah. Okay, bye.